this is example. So for this example, it's saying that chlorination of methane is shown by the following reaction. So CH4 is your methane. You add with chlorine gas, you'll get chloromethane plus HCl, hydrochloric acid. If the feed contains 40% of CH4, 50% of Cl2, and 10% of N2, and 67% of the limiting reactant is converted, calculate the product composition. Okay, so here whatever a rule of thumb that you need to understand here is that whatever composition usually given for a reactive system, unless it is mentioned specifically in the question, we can just say that all these are mole composition. Okay, so this is actually your mole fraction 0 0.4, 0 0.5 and 0 0.1. And we also have a conversion which is 67% of the emitting reactant. So again, for any reactive system equation, we need to first check whether this equation is balanced or not, because most of the time we'll be using the stoichiometric coefficient. So by looking at it, I know that I have one carbon here and one carbon, 4 hydrogen, so 3 plus 1 is 4 hydrogen. I have 2 chlorine, so 1 chlorine here, 1 chlorine here, so this equation is actually balanced, so we can start to solve our question. And then since no value is given, so we can just, I put my basis here, is equal to 100 mole of feed, because I know that this is composition in mole. So let's say, first of all, now we know the composition, we know the basis, so we can just draw and label our flow chart. Let's say this is your reactor. We have feed coming in, so I know I have 100 mole here, which is 0.4 is methane, 0.5 is chlorine, and 0.1 is nitrogen. And then coming out from your reaction, I know from my reaction I have a product of chloromethane, so CH3Cl, and then I have HCl. And since I know that I have a conversion given to me, so meaning that I already know that not all of my reactant will be converted, will be consumed and produce product. So I know that I will have leftover unreacted methane, CH4. I have unreacted chlorine gas, and of course I will have nitrogen here, because nitrogen is an inert gas. So I can label them, since I don't know anything here, I can just label them as this one is N1, this one is N2, this one is N3, N4, and N5. So here I'm using the symbol of N because all of this is in mole. Okay, so now I have labeled everything, and I also know that my percentage conversion is equal to 67% of the limiting reactant. So before I can find how much product is left, I must find which one is my limiting reactant. It can either be methane or chlorine. Definitely it's not nitrogen, because nitrogen is inert and does not involve in our reaction. So it's either methane or chlorine. Now if I were to look at, so let me just write again the reaction. CH4 plus Cl2 will get CH3Cl plus HCl. So if I look at my stoichiometric here, 1 mole of CH4 will react with 1 mole of chlorine gas, right? And based on this value, 0.4 times 100, I know that I have a total of 40 mole of methane. in my reaction. So if 40 mole of methane is present, then I know that 40 mole of methane will react with 40 mole of chlorine. Now, based on this ratio, I know that chlorine I have 0.5 times 100 is 50. So even if all methane is reacted, I only need 40 mole of chlorine, whereas I have 50 mole of chlorine. So based on this, I can say that CH4 is my limiting reactant. Okay, so now I know that my methane is my limiting reactant. So based on this, I can use this value now. So if we remember the formula of conversion, percentage conversion is actually equal to mole reacted over mole fat times 100. So I know that the value here is 67, right? So this is the value 67. So 67 is equal to mole reacted. I don't know. This is the value that I want to find. Mole fat is 40 mole times 100. So I'll get mole reacted is equal to 26.8 mole. Okay, so this is the mole of methane that is reacted. So now that we have found all these things, so we can actually start to do our material balance. So let's say we do material balance on methane first. Okay, so I'll say I'll do balance on methane. Okay, so remember our equation just now. General equation is input minus output plus generation minus consumption is equal to 0. So this is the general equation, and whenever you are doing molecular species balance, you must always use this equation. So first of all, let us look at for methane. We have our input, which is our 40 mole. We have output because there's some methane unreacted, so we can put here our output value we put here is N3, so we can just label here is N3, plus do we have generation? We don't have generation because there is no new methane generated in our product, so no generation term. We can cancel out generation term, and we also definitely will have consumption term because this is the amount of mole of methane reacted or consumed. So we have the value of 26.8 is equal to 0. And we can solve this equation. We can get our value of N3 is equal to 13.2 mole. Okay, so this is the first balance on methane. So then we continue, we can say that we can do balance on our product or our reactant. So let's say we were saying we want to do balance on our chlorine gas. Okay, so again the same thing, input minus output plus generation. This right here, input minus output plus generation minus consumption is equal to 0. So definitely we know that we have our input of 50 mole minus definitely we have our output, and we also have labeled our output to be N4, right? N4. There's no generation because chlorine is being consumed, so no generation, but we do have our consumption and it is equal to 0. Now, how do we find our consumption? So this is where we'll be using our stoichiometric coefficient and ratio. So we know that 1 mole of methane will react with 1 mole of chlorine gas. right? And we know that the amount of methane reacted was 26.8 mole of methane. Definitely will react because the ratio is 1 to 1, so it will react with 26.8 mole of chlorine. So definitely we can just say that our consumption here is 26.8. So I can write here again my equation, 50 minus N4 minus 26.8 is equal to 0. And then I can find the value of N4 is equal to 23.2 mole. Okay, so I have done the balance for chlorine. Now I can do balance on my product. So we can say that balance on chloromethane. CH3Cl. Again the equation, input minus output plus generation minus consumption is equal to 0. Now if you look at our equation just now, there is no chloromethane in our input, right? Initially we do not have any chloromethane. Definitely we have output because this is our product. Definitely we have generation because initially we don't have any chloromethane, but after the reaction some chloromethane was generated, and definitely if there is generation there is no consumption. So we can say that output is equal to generation, and our output we have labeled it as N1. So N1 is equal to generation. So how do we find our generation? The same thing, we use our stoichiometric coefficient and stoichiometric ratio. So we say that 1 mole of methane will generate 1 mole of chloromethane. So if 26.8 mole of methane is consumed, then it will produce 26.8 mole of chloromethane. So the generation of chloromethane is equal to 26.8, and we can say that our N1 value is equal to 26.8 mole. Okay, so we have done for chloromethane, and we can do the same thing for balance on HCl. So since HCl is also a product, I can just, using this same reaction, I can say that our output is equal to generation, and I have labeled HCl as my N2. So N2 is equal to generation, and I can use the same stoichiometric relation here. 1 mole of methane will produce 1 mole of HCl, and if I have 26.8 mole of methane reacting, then I will have 26.8 mole of HCl generated. So I can just say that my N2 is also equal to 26.8 mole. Okay, so we have found N1, N2, N3, N4. Now the only thing left is our, so if you look at here, we have our N5. Now N5 will be the easiest way for you to find, because whatever nitrogen is going in is the nitrogen coming out. Since nitrogen is not reacting in our reaction, so we can just say that, we can just write here, balance for nitrogen. Okay, again the equation, input minus output plus generation minus consumption is equal to 0. Since there is N2 is not involved in our reaction, so no generation, no consumption. Input is equal to output, and our output we label as N5, and the input of nitrogen is 0.1 times 100, so we can get our N5 value is 10 mole. So if we go back here, we have found the value of N1 is equal to 26.8, N2 is equal to 26.8, N3 is equal to 13.2, and our N4 is equal to 23.2, and our N5 is equal to 10 mole. So we have actually done the balance and we have found the composition of our product. Okay, so that is how we solve our material balance using molecular species balance. Now, if you say that I don't want to use molecular species balance, but I actually want to use my atomic balance, can you do that? Yes, you can do that. So no problem. So let us see what is our atomic balance. So I'll just write again the equation. CH4 plus Cl2 will get CH3Cl plus HCl. So first of all, you need to identify what atoms you have in your reaction. So from here, I can say that I have carbon atom, I have hydrogen atom, and I have chlorine atom. So these are the only three atoms involved in our reaction. And then we also have nitrogen atom. But nitrogen, since it is not reacting, so we don't have to actually involve in our atomic balance. So we can just straight away say input is equal to output, and we can get our value of N5 is equal to 10 mole. So we want to do balance on these three units. So if you were to start, of course, we have to start again finding our limiting reactant and finding how much of methane is consumed. So if you look at here, and then I'll just write here, N1 is for our chloromethane, N2 is for our HCl, N3 is for our methane, N4 is for our chlorine gas, and N5 here is for our N2. We already know N5 is equal to 10. So now we want to do, let's say we want to do balance on carbon. So balance on carbon. So if we are using atomic balance, input is equal to output. This is the only thing you need to know. So if let's say input equal to output, so we want to know in our input side how many carbon we have, and in our output side how many carbon we have. So we have 1 mole of carbon in 1 mole of, so 1 mole of carbon in 1 mole of methane, right? And then we know the mole of methane is equal to 40 mole. Okay, and then we don't have any more carbon on our input side, so it is equal to, we have carbon here, so we have 1 mole of carbon in 1 mole of chloromethane, and then the mole of chloromethane is N1, so we can say N1 mole of chloromethane. We can say here this one is N1 mole of methane. So based on here, do we have any more carbon? Yes, we do, because we say that if you look at here, you have carbon here, and we also have carbon, the unreacted carbon, whatever left in our CH4. So we can say that, let me just, okay, plus 1 mole of carbon in 1 mole of unreacted methane, and the mole for that is N3 mole of methane. Right? So if we solve this one, we'll get the equation we get is 40 is equal to N1 plus N3. Okay, so this is our first equation. Okay, so we can do the same thing, balance on hydrogen. So again, looking at our reaction, so we say in our input side, I have 4 mole of hydrogen in every 1 mole of methane. And I know that the mole of methane is equal to 40 mole of methane is equal to, if you look at our, I think it's easier if I just draw a flow chart here. It's easy for me to understand. Okay, so we have CH4, Cl2, and 2, and then coming out we have CH3Cl, HCl, CH4, Cl2, and N2. Okay, so we just follow this flow chart. So on our input side, we have 4 mole of hydrogen in 1 mole of methane. That is all the hydrogen we have. And in our product side, we have 3 mole of hydrogen in every 1 mole of CH3Cl, and then the mole of CH3Cl is N1 mole CH3Cl, and then we also have hydrogen in our HCl. So we can see here plus 1 mole of hydrogen in every 1 mole of HCl, and then the mole of HCl is N2, right? N2, and then we say that we also have hydrogen in our unreacted methane. So plus 4 mole of hydrogen in 1 mole of CH4, and then the mole is N3. So when we do this, we'll get an equation is equal to 160 is equal to 3N1 plus N2 plus 4N3. That is the balance on hydrogen. So if we do balance on our chlorine, so we know that from our flowchart here, okay, we have 2 mole of chlorine in 1 mole of chlorine gas, right? So I can just write here 2 mole of Cl in every 1 mole of Cl2, and then I know initially I have 50 mole of chlorine. So there is no Cl, any Cl in our product, in our input side. So you can say it is equal to, in our product we have 1 Cl in 1 chloromethane, 1 Cl in 1 HCl, and 2 Cl in our unreacted chlorine. So we can say 1 mole Cl in every 1 mole of CH3Cl, and then the value is N1 plus 1 mole of Cl in every 1 mole of HCl, and the mole is N2. plus 2 mole of Cl in every 1 mole of Cl2, and the mole value is N4. Okay, so if we do the balance, we'll get 50 times 2 is 100, right? 100 is equal to N1 plus N2 plus 2 and 4. So we have 3 equations now. So if I were to write again all the equations, 160 is equal to 3N1 plus N2 plus 4 and 3. And the first equation was 40 is equal to N1 plus N3. So these are the 3 equations that we have, and we can solve these and we can find the value of N1, N2 and N3. So how do we do that? So we know that we have our conversion value, right? We know that our conversion is 67%. So we can say that 67 is equal to mole reacted over 40 times 100, right? This is the formula that we're using just now. And for mole reacted here means that, so 67 here is equal to, mole reacted here means that we have our initial mole, which is 40, minus whatever we have left in our system. So if you minus whatever left is N3 over 40 times 100. So we can get the value of N3 is equal to actually the same value just now, which is 13.2 mole. And then once you have gotten the value of N3, you can substitute the value of into here and you can get the value of N1. And then you can substitute the value of N1 and N3 to get the value of N2. Once you have the value of N2, you can substitute here N1 and N2 to get the value of N4. And you should be able to get the value of N1 until N5, same as the value that we calculated using our molecular species balance. So these are 2 methods for you to solve using molecular species balance or atomic balance. Now if you see here, the atomic balance looks a little bit more complicated than your molecular species balance. Why? Because this is a simple reaction. So if it's a system like this, and if you feel that you are more comfortable in solving using molecular species balance, you can solve the question using molecular species balance instead of atomic species balance. But at the end of the day, you should get the same answer.